Hello. Going to try a little experiment today. Going to start reading through parts of The Beginning of Infinity. Just the first chapter. I've seen at least one other Aussie doing this with a different series of books. I don't know if it'll be useful. I thought I'd try it just as an experiment. Sort of thinking out loud, I guess. And just commenting on some of my favourite parts of the book. By doing so, it kind of clarifies my own thoughts about things. That's one thing. The other thing also, there is a sense in the critical rationalist community that there's a lot of bad ideas out there, or false ideas, that get a lot of traction in an undeserved kind of way, while the ideas of Popper and Deutsch, for example, don't. And so this might go some way to addressing that. So in the case of Popper, we've got, of course, the open society and its enemies, and the fact that people misunderstand what democracy is about. We have the idea on the ascendancy that Bayesianism is true, which I've commented recently is essentially inductivism in a cheap tuxedo. So we thought we'd dispatched with inductivism. We hadn't. It's come back stronger than ever, in a sense. And it has real practical problems. It means that science ends up being a quest for formulae, mathematical formulae, that in some sense can statistically describe certain trends that we have. So rather than being a kind of problem-solving creative exercise, people are diverted into looking for statistical patterns. And this is very useful in some areas, there's no doubt. But when all of science appears to be on board with thinking that this is the way in which science works, it can cause delays. It can cause problems. But I digress. I'm here today to talk about the Beginning of Infinity. And I'm going to start with Chapter 1, The Reach of Explanations, and there's thunder outside. And my purpose here is just to read out some of my favourite parts of each chapter, not to serve as a summary. David, in fact, did this himself at the conclusion of each chapter. He wrote two forms of summary. One is the meanings of the beginning of infinity found in this chapter, and an actual summary at the end of each chapter. So if you were looking for the crib notes version of the beginning of infinity, you can simply read the summaries at the end of each chapter. It's not a recommended way to try and understand some of the subtleties of these ideas, but certainly you can go a long way of understanding the philosophy by doing that rather than doing nothing. So let me begin. Partway through chapter 1, David says, "How do we know? One of the most remarkable things about science is the contrast between the enormous reach and power of our best theories and the precarious local means by which we create them. No human has ever been to the surface of a star, let alone visited the core where the transmutation happens and the energy is produced. Yet we see those cold dots in our sky and know that we are looking at the white-hot surfaces of distant nuclear furnaces. Physically, that experience consists of nothing other than our brains responding to electrical impulses from our eyes, and eyes can detect only light that is inside them at the time. The fact that the light was emitted very far away and long ago, and that much more was happening there than just the emission of light, those are not things that we see. We know them only from theory. Scientific theories are explanations, assertions about what is out there and how it behaves. Where do these theories come from? For most of the history of science, it was mistakenly believed that we derive them from the evidence of our senses, a philosophical doctrine known as empiricism." Now, he then provides, or in the beginning of infinity, provides a diagram. A diagram has in form it is, in the first box it says sensory experiences. There's an arrow which is labelled derivation, such as extrapolation, generalization, or induction. And that leads to another box that says theories, knowledge of reality. So this is the idea of empiricism, that we go out into the world, we use our senses to read a book of nature in a sense. I'll continue. For example, the Philosopher John Locke wrote in 1689 that the mind is like white paper onto which sensory experience writes, and that is where all of our knowledge of the physical world comes from. Another empiricist metaphor was that one could read knowledge from the book of nature by making observations. Either way, the discoverer of knowledge is its passive recipient, not its creator. But in reality, scientific theories are not derived from anything. We do not read them in nature, nor does nature write them into us. They are guesses, bold conjectures. Human minds create them by rearranging, combining, altering, and adding to existing ideas with the intention of improving upon them. We do not begin with white paper at birth, but with inborn expectations and intentions, and an innate ability to improve upon them, using thought and experience. Experience is indeed essential to science, but its role is different from that supposed by empiricism. It is not the source from which theories are derived. Its main use is to choose between theories that have already been guessed. This is what learning from experience is. However, that was not properly understood until the mid-20th century with the work of the philosopher Karl Popper. So historically, it was empiricism that first provided a plausible defense for experimental science as we now know it. Empiricist philosophers criticized and rejected traditional approaches to knowledge, such as deference to authority of holy books and other ancient writings, as well as human authorities such as priests and academics, and belief in traditional law, rules of thumb, and hearsay. Empiricism also contradicted the imposing and surprisingly persistent idea that the senses are little more than sources of error to be ignored. And it was optimistic, being all about obtaining new knowledge in contrast with the medieval fatalism that it expected everything important to be known already. Thus, despite being quite wrong about where scientific knowledge comes from, empiricism was a great step forward in both the philosophy and history of science. Nevertheless, the question that skeptics, friendly and unfriendly, raised from the outset always remained: how can knowledge of what has not been experienced possibly be derived from what has? What sort of thinking could possibly constitute a valid derivation of the one from the other? No one would expect to deduce the geography of Mars from the map of the Earth, so why should we expect to be able to learn about physics on Mars from experiments done on Earth? Evidently, logical deduction alone would not do, because there is a logical gap. No amount of deduction applied to statements describing a set of experiences can reach a conclusion about anything other than those experiences. The conventional wisdom was that the key is repetition. If one repeatedly has similar experiences under similar circumstances, then one is supposed to extrapolate or generalize that pattern and predict that it will continue. For example, why do we expect the sun to rise tomorrow morning? Because in the past, so the argument goes, we have seen it do so whenever we have looked at the morning sky. From this, we supposedly derive the theory that under similar circumstances, we shall always have that experience, or that we probably shall. On each occasion, when the prediction comes true, and provided that it never fails, the probability that it will always come true is supposed to increase. Thus, one supposedly obtains ever more reliable knowledge of the future from the past, and of the general from the particular. That alleged process was called inductive inference, or induction. And the doctrine that scientific theories are obtained in that way is called inductivism. To bridge the logical gap, some inductivists imagine there is a principle of nature, the principle of induction, that makes inductive inferences likely to be true. The future will resemble the past is one popular version of this. And one could add that the distant resembles the near, the unseen resembles the seen, and so on. But no one has ever managed to formulate a principle of induction that is usable in practice for obtaining theories from experiences. Historically, criticism of inductivism has focused on that failure and on the logical gap that cannot be bridged. But that lets inductivism off far too lightly, for it concedes inductivism's two most serious misconceptions. First, inductivism purports to explain how science obtains predictions about experiences. But most of our theoretical knowledge simply does not take that form. Scientific theories are about reality, most of which does not consist of anyone's experiences. Astrophysics is not primarily about us, what we shall see if we look at the sky, but rather about what stars are, their composition and what makes them shine, and how they are formed, and the universal laws of physics under which they happened. Most of that has never been observed. No one has experienced a billion years or a light year. No one could have been present at the Big Bang. No one will ever touch a law of physics except in their minds through theories. All our prediction of how things will look are deduced from such explanations of how things are. So inductivism fails even to address how we can know about stars and the universe as distinct from just dots in the sky. The second fundamental misconception in inductivism is that scientific theories predict that the future will resemble the past and that the unseen resembles the seen and so on, or that it probably will. But in reality, the future is unlike the past, the unseen very different from the seen. Science often predicts and brings about phenomena spectacularly different from anything that has been experienced before. For millennia, people dreamed about flying, but they experienced only falling. Then they discovered good explanatory theories about flying, and then they flew in that order. So that's a part, just as an aside. Yeah, this is me. This is not from the book. That David references in his TED Talk, one of his TED Talks. These first 3 chapters provide much of the material for a new way to explain explanation. That TED Talk there. I'll continue. Before 1945, no human being had ever observed a nuclear fission atomic bomb explosion. There may never have been one in the history of the universe. Yet the first such explosion, and the conditions under which it would occur, had been accurately predicted, but not from the assumption that the future would be like the past. Even sunrise, that favourite example of inductivists, is not always observed every 24 hours. When viewed from orbit, it may happen every 90 minutes or not at all. And that was known from theory long before anyone had ever orbited the Earth. In fact, it only happens 24 hours very rarely, isn't it? Near the equator or on a mid-year solstice or something like that. If you go to Antarctica or anywhere inside the Arctic Circle or the Antarctic Circle, you'll find that the sun's not setting, or it's not rising. I'll continue. It is no defence of inductivism to point out that in all these cases the future still does resemble the past in the sense that it obeys the same underlying laws of nature. For that is an empty statement. Any purported law of nature, true or false, about the future and the past is a claim that they resemble each other by both conforming to that law. So that version of the principle of induction could not be used to derive any theory or prediction from experience or anything else. So this is, again, a world-class philosopher explaining in detail why it is that induction cannot possibly work. Not only that it isn't actually the thing that allows scientific theories to be constructed, it's not even a thing that allows you to construct any kind of knowledge whatsoever. It doesn't exist. Induction is irrationality. It's a way of generalizing. What is surprising to me is that professional philosophers seem to enjoy teaching their students logical fallacies, and they understand logical fallacies quite well. One of these logical fallacies is the fallacy of hasty generalization. This is the idea that if you see something a number of times, that you conclude that therefore it's a general rule. This is the kind of faulty reasoning that leads to things like racism, let's say. It's where you observe a particular behaviour amongst a certain group of people that look the same, and you form the conclusion that therefore it applies to all people that look that way. It is the assumption that if you see a bunch of white swans, that you assume that therefore all swans are white. based on a limited number of observations. But how hasty do you have to be for a generalization to be hasty? Well, I would say it's impossible to do an exhaustive search or to come up with a regularly occurring phenomenon such that it has occurred a sufficient number of times for you to have any degree of confidence that it will continue into the future. It's not like observing the same thing 10 times in a row means you are 10 times less confident than if you observe the thing 100 times in a row. It doesn't matter if you observe things every single day forever, for a long, long time. It doesn't mean that that thing is not going to be contravened the very next day. David actually goes on to use his example of up until December 31st, 1999, he'd only ever experienced in the year, he'd only ever experienced a 1-9. He'd never experienced a 2-0. But his experience throughout his life of seeing a 19 in front of the year's date, 1991, 1992, 1993, etc., up to 1999, he knew that that expectation of a 1-9 was about to be refuted, namely on January 1st, 2000. This is always the case. We cannot know, especially in science, out there in the physical world, that the phenomena that you've seen repeating itself isn't part of a much larger, more complex phenomena where, at any moment, it's going to reveal itself to be utterly false. Let me go back to the beginning of infinity. So David continues later. I'm cutting out a fair bit here. Empiricism never did achieve its aim of liberating science from authority. It denied the legitimacy of traditional authorities, and that was salutary. But unfortunately, it did this by setting up two other false authorities: sensory experience and whatever fictitious process of derivation, such as induction, one imagines is used to extract theories from experience. The misconception that knowledge needs authority to be genuine or reliable dates back to antiquity, and it still prevails. To this day, most courses in the philosophy of knowledge teach that knowledge is some form of justified true belief, where justified means designated as true, or at least probable, by reference to some authoritative source or touchstone of knowledge. Thus, how do we know is transformed into by what authority do we claim? The latter question is a chimera that may well have wasted more philosophers' time and effort than any other idea. It converts the quest for truth into a quest for certainty, a feeling, or for endorsement, a social status. This misconception is called justificationism. The opposing position, namely the recognition that there are no authoritative sources of knowledge, nor any reliable means of justifying ideas as being true or probable, is called fallibilism. To believers in the justified true theory of knowledge, the justified true belief theory of knowledge, this recognition is the occasion for despair or cynicism, because to them it means that knowledge is unobtainable. But to those of us for whom creating knowledge means understanding better what is really there and how it really behaves and why, fallibilism is part of the very means by which this is achieved. Fallibilists expect even their best and most fundamental explanations to contain misconceptions in addition to truth, and so they are predisposed to try to change them for the better. In contrast, the logic of justificationism is to seek, and typically to believe that one has found, ways of securing ideas against change. Moreover, the logic of fallibilism is that one not only seeks to correct the misconceptions of the past, but hopes in the future to find and change mistaken ideas that no one today questions or finds problematic. So it is fallibilism, not mere rejection of authority, that is essential for the initiation of unlimited knowledge growth, the beginning of infinity. Okay, so yes, this is a wonderful defense of fallibilism. I think that if there's a philosophy in a sense, that unites many people who follow the work of David Deutsch. It is this idea of fallibilism. And I think this is one of the strongest defenses that we find anywhere. David's spoken about it online in various places. There's the Nautilus interview, I think, does a wonderful job of that. I think he might have mentioned it in his Closer to Truth interviews as well. So this concept that because you can be wrong, and you can be wrong about the truth, that admits the truth is... that admits that there is an objective truth, because you can be wrong about it. And so we take the idea of realism seriously, that there is an objective reality out there, and not all claims to that reality, not all truth claims about that reality stand on equal footing. Some of them can be shown or already have shown to be false. Some of them haven't yet been shown to be false but are good explanations. And this idea of fallibilism is that because it is people who are constructing the knowledge and people are prone to error, that we can never be sure that we've found the perfect theory. It's always going to be riddled with errors in ways we don't know, and therefore subject to improvement, whereby if we can make those improvements, we've made progress. And objective progress, because we've corrected some errors. And so the new theory that we have, that doesn't have the errors of the old theory, is objectively better. So we're moving in a particular direction. And this is all underpinned by fallibilism, the simple acknowledgement that for any claim that is made by human beings, or by people generally, we can be wrong about it. There is no royal road to truth. And anyone who claims that they have possession of the absolute final truth have to admit that they're human. And even if an infallible source has provided them with information that is guaranteed to be true, it is them that is now interpreting it. It is them that is now reporting to you what this truth is. And therefore their words are fallible. Their words could be in error. Their memory could be in error. A whole bunch of things could be going wrong. Even if the source from which they're claiming to have gained this perfect knowledge was itself perfect. Because they're reporting it to you and they're fallible. And fallibilism is about people. It's not about supernatural entities, although we could apply it there as well. That if a supernatural entity tries to claim perfect knowledge, then we are quite entitled to ask, by what means? By what means has this inerrant knowledge come? And when you hear it from the inerrant source, how do you know you're hearing it inerrantly? Okay, back to the book. David goes on. However, rebellion against authority cannot by itself be what made the difference. Authorities have been rejected many times in history, and only rarely has any lasting good come of it. The usual sequel has merely been that new authorities replace the old. What was needed for the sustained rapid growth of knowledge was a tradition of criticism. Before the Enlightenment, that was a very rare sort of tradition. Usually, the whole point of a tradition was to keep things the same. So let me pause here. There are a number of genuine discoveries that David Deutsch has made in philosophy, in epistemology, in history, that appear in the beginning of infinity. They appear in the fabric of reality as well, some of them. But here in the beginning of infinity, we have some truly groundbreaking ways of attempting to understand reality, humanity, knowledge as a whole. And these ideas, how can we say this, have not thus far reached as many people as they deserve to have reached yet. And this one in particular is such a useful starting point for any historian. Anyone who's interested in history could benefit from really trying to get to the heart of this idea of tradition of criticism. This idea in particular, this idea of a tradition of criticism, is an idea that could really inform history, or the study of history, or the study of sociology. perhaps even study of psychology to some extent as well. This idea that criticism is a thing that allows progress, and a tradition of criticism is something that is an explanation for the reasons why there was a stark difference between the year 1000 and the year 2000. Whereas the year 1000 was very much like the year 0, and very much like the year 1000 BC, which was very much like the year 10,000 BC. For the majority of human history, things were in stasis. Things were the same. There wasn't much change going on. And then something remarkable happened. And it's called the Enlightenment, and it led to the Industrial Revolution. But what are the philosophical underpinnings that caused these massive transformations? Now, we can talk about, oh, well, science arrived, and there was this idea of having science being about testable ideas, and we discovered things like steam engines. Very well. These are effects of a deeper philosophical phenomenon. And the philosophical phenomenon is, as David explains here, a tradition of criticism. Let me continue with the beginning of infinity. Thus, the Enlightenment was a revolution in how people sought knowledge by trying not to rely on authority. That is the context in which empiricism, purporting to rely solely on the senses for knowledge, played such a salutary historical role, despite being fundamentally false, and even authoritative in its conception of how science works. One consequence of this tradition of criticism was the emergence of a methodological rule that a scientific theory must be testable, though this was not made explicit at first. That is to say, the theory must make predictions which, if the theory were false, could be contradicted by the outcome of some possible observation. Thus, although scientific theories are not derived from experience, they can be tested by experience, by observation or experiment. For example, before the discovery of radioactivity, chemists had believed, and had verified in countless experiments, that transmutation is impossible. Rutherford and Soddy boldly conjectured that uranium spontaneously transmutes into other elements. Then, by demonstrating the creation of the element radium in a sealed container of uranium, they refuted the prevailing theory and science progressed. They were able to do that because that earlier theory was testable. It was possible to test for the presence of radium. In contrast, the ancient theory that all matter is composed of a combination of elements, including earth, air, fire, and water, was untestable because it did not include any way of testing for the presence of those components. So it could never be refuted by experiment. Hence, it could never be, and never was, improved upon through experiment. The Enlightenment was at root a philosophical change. The physicist Galileo Galilei was perhaps the first to understand the importance of experimental tests, which he called sementi, meaning trials by ordeal, as distinct from other forms of experiment and observation, which can more easily be mistaken for reading from the book of nature. Testability is now generally accepted as the defining characteristic of the scientific method. Popper called it the criterion of demarcation between science and non-science. Nevertheless, testability cannot have been the decisive factor in the scientific revolution either. Contrary to what is often said, testable predictions had always been quite common. Every traditional rule of thumb for making a flint blade or a campfire is testable. Every would-be prophet who claims that the sun will go out next Tuesday has a testable theory. So does every gambler who has a hunch that this is my lucky night, I can feel it. So what is the vital, progress-enabling ingredient that is present in science, but absent from the testable theories of the prophet and the gambler? Well, pausing here. Sometimes I'm left a little bit speechless. I can read this book 100 times and still come across things where I almost get misty-eyed because it is a remarkably dense work where you come across these things that no one else previously has said. Some people may know I was forced at university to read all sorts of philosophy books that didn't much strike me as interesting. Some were. But what you do find is even when you pick up a good book, let's say Descartes' Meditations, I really liked it. 5 meditations, it's only a short bit, but there's essentially 1 or 2 ideas in there that are kind of, wow, that's amazing. And then the rest is fluff. Whereas this work here, and here's another example, makes this groundbreaking claim that's true and which still hasn't made itself reach into the zeitgeist. So let me just summarize what I heard David say there. Popper made the claim, and many people seem to agree, that testability is this thing that demarcates science from non-science. And he's right. However, testable theories have always existed. There have always been testable theories around. A caveman who's trying to make a better flint blade has a testable theory when he makes his new flint blade. If it actually turns out to be better, then he keeps that one and he refutes the old one. If it's not better, then he refutes the new one and he keeps the old one. So, testability can't be enough to say what the purpose of science is. There has to be more to science than this. Testability's got something to do with it, but it's not the whole story. David is about to go on to explain his improvement. And I don't want to rely on authority, okay? But those of us who have been looking into the philosophy of science for a long time have read people who have criticised Popper, or people who claim to have improved Popper. We would readily admit if we can find someone who has done either of those things. But it is almost never the case. And so when presented with things like Bayesianism, we shrug our shoulders because we realise that Popper already refuted inductivism. And anyone who says inductivism works, or that a variation on inductivism like Bayesianism might be useful for science, we've heard this argument before. Popper heard these arguments. These arguments have been going on for decades. We've read the surrounding material and we remain unconvinced. But then when someone like David Deutsch comes along, and he's not actually saying here in the book, but maybe he said it once, he's not actually saying he's improved Popper, but he does improve Popper. He does it right here, he does it explicitly, he's about to do it right now. So it's an amazing accomplishment. And so let's just persevere. I'll go into the next paragraph. The reason that testability is not enough is that prediction is not, and cannot be, the purpose of science. Consider an audience watching a conjuring trick. The problem facing them has much the same logic as a scientific problem. Although in nature there is no conjurer trying to deceive us intentionally, we can be mystified in both cases for essentially the same reason. Appearances are not self-explanatory. If the explanation of a conjuring trick were evident in its appearance, there would be no trick. If the explanations of physical phenomena were evident in their appearance, empiricism would be true, and there would be no need for science as we know it. The problem is not to predict the trick's appearance. I may, for instance, predict that if a conjurer seems to place various balls under various cups, those cups will later appear to be empty. And I may predict that if the conjurer appears to saw someone in half, that person will later appear on stage unharmed. Those are testable predictions. I may experience many conjuring shows and see my predictions vindicated every time, but that does not even address, let alone solve, the problem of how the trick works. Solving it requires an explanation, a statement of the reality that accounts for the appearance. Okay, so now I'm skipping a lot of Chapter 1, the reach of explanation, so I encourage people to actually go to Chapter 1 and read the whole thing. And he speaks about science and he speaks about progress and how progress has happened in the past. And now let me go back to the book. But even testable explanatory theories cannot be the crucial ingredient that made the difference between no progress and progress. For they too have always been common. Consider, for example, the ancient Greek myth for explaining the onset of winter. Long ago, Hades, god of the underworld, kidnapped and raped Persephone, goddess of spring. Then Persephone's mother, Demeter, goddess of the earth and agriculture, negotiated a contract for her daughter's release which specified that Persephone would marry Hades and eat a magic seed that would compel her to visit him once a year thereafter. Whenever Persephone was away fulfilling his obligation, Demeter became sad and would command the world to become cold and bleak so that nothing could grow. And this is the wonderful example that David uses in his TED Talk, and talks about how, because it didn't need to be Demeter, it could have indeed been some other god. It could have been someone different to Persephone. It didn't need to be a marriage contract. It could have been any other contract. The specific parts of the theory that explain the seasons on this Greek myth explanation are easy to vary. Let me read a part where he speaks about this in particular. So with myths, the reason why those myths are so easily variable is that their details are barely connected to the details of the phenomena. Nothing in the problem of why winter happens is addressed by postulating specifically a marriage contract, or a magic seed, or the gods Persephone, Hades and Demeter, or Freya. Whenever a wide range of variant theories can account equally well for the phenomena they are trying to explain, there is no reason to prefer one of them over the others. So advocating a particular one in preference to the others is irrational. Skipping a bit. In general, when theories are easily variable in the sense I have described, experimental testing is almost useless for correcting their errors. I call such theories bad explanations. Being proved wrong by experiment and changing the theories to other bad explanations does not get their holders one jot closer to the truth. Because explanation plays this central role in science, and because testability is of little use in the case of bad explanations, I myself prefer to call myths, superstitions, and similar theories unscientific, even when they make testable predictions. But it does not matter what terminology you use, so long as it does not lead you to conclude that there is something worthwhile about the Persephone myth, or the prophet's apocalyptic theory, or the gambler's delusion, just because it is testable. Nor is a person capable of making progress merely by the virtue of being willing to drop a theory when it is refuted. One must also be seeking a better explanation of the relevant phenomena. That is the scientific frame of mind. Wonderful. So here David is saying that even if you've got a testable prediction, that doesn't mean that you are entitled to be referred to as a scientific theory. I think this is a well expressed way of understanding Popper in a new way, more explicitly than perhaps Popper himself was able to explain. Continue. As the physicist Richard Feynman said, science is what we have learned about how to keep from fooling ourselves. By adopting easily variable explanations, the gambler and the prophet are ensuring that they will be able to continue fooling themselves no matter what happens. Just as thoroughly as if they had adopted untestable theories, they are insulating themselves from facing evidence that they are mistaken about what is really there in the physical world. The quest for good explanations is, I believe, the basic regulating principle not only of science but of the Enlightenment generally. And when he says Enlightenment generally, he means through to today. He's not just talking about that shortish period that led to the Industrial Revolution in the past. He's talking about the beginning of the Enlightenment continuing through to today. So he would say the Enlightenment is still happening now, and I would agree. It is the feature, this quest for good explanations, it is the feature that distinguishes those approaches to knowledge from all others, and it implies all those other conditions for scientific progress I have discussed. It trivially implies that prediction alone is insufficient. Somewhat less trivially, it leads to the rejection of authority, because if we adopt a theory on authority, that means that we would also have accepted a range of different theories on authority. And hence it also implies the need for a tradition of criticism. It also implies a methodological rule, a criterion for reality. Namely, that we should conclude that a particular thing is real if and only if it figures in our best explanation of something. This is also mentioned in The Fabric of Reality. I think it talks about it as being something like Dr. Johnston's criterion. Hold on. Yes, so there is a section in The Fabric of Reality, of course, about precisely this. Chapter 4 there is called Criteria for Reality, and the discussion there is along the lines of Dr. Johnson's understanding of this phenomena of things kicking back in reality. So if they kick back, that means they act in autonomous, unpredictable ways, in ways that you can't predict. beforehand. So you have to go out and test things, and this doesn't mean only science. If you're investigating anything and it reacts in a way that you didn't predict, then you know you've got something real. Okay. Now David goes on to write about the actual explanation of seasons and how the Earth is on a tilt. And he says, that is a good explanation. Hard to vary because all its details play a functional role. And that is important as well. So a good explanation is hard to vary because all of its details play a functional role. In the axis tilt theory of the Earth, you can't tilt the axis by more than what it is actually tilted, because if you did, the seasons would be different than what they are. Good explanations are often strikingly simple or elegant, as I shall discuss in chapter 14. Also, a common way in which an explanation can be bad is by containing superfluous features or arbitrariness, and sometimes removing those yields a good explanation. This has given rise to the misconception known as Occam's razor, named after the 14th century philosopher William of Ockham, but dating back to antiquity. Namely, that one should always seek the simplest explanation. One statement of it is, do not multiply assumptions beyond necessity. And I think this is what David used in The Fabric of Reality. However, there are plenty of very simple explanations that are nonetheless easy to vary, such as Demeter did it, and while assumptions beyond necessity make a theory bad by definition, there have been many mistaken ideas of what is necessary in a theory. Instrumentalism, for instance, considers explanation itself unnecessary, and so do many other bad philosophies of science, as I shall discuss in chapter 12. When a formerly good explanation has been falsified by new observations, it is no longer a good explanation, because the problem has expanded to include those observations. Thus, the standard scientific methodology of dropping theories when refuted by experiment is implied by the requirement for good explanations. The best explanations are the ones that are most constrained by existing knowledge, including other good explanations as well as other knowledge of the phenomena to be explained. That is why testable explanations that have passed stringent tests become extremely good explanations, which is in turn why the maximum of testability promotes the growth of knowledge in science. Conjectures are the products of creative imagination, but the problem with imagination is that it can create fiction much more easily than truth. As I have suggested, historically, virtually all human attempts to explain experience in terms of a wider reality have indeed been fiction in the form of myths, dogma, and mistaken common sense, and the rule of testability is an insufficient check on such mistakes. But the quest for good explanations does the job. Inventing falsehoods is easy, and therefore they are easy to vary once found. Discovering good explanations is hard, but the harder they are to find, the harder they are to vary once found. The ideal that explanatory science strives for is nicely described by the quotation from Wheeler, with which I began this chapter. Behind it all is surely an idea so simple, so beautiful, that when we grasp it in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? Now we shall see how this explanation-based conception of science answers the question that I asked above. How do we know so much about unfamiliar aspects of reality? Okay, so again, here we have it. Here we have the claim that testability is not a sufficient bulwark against irrationality, but the quest for good explanations is. The quest for good explanations, good explanations being hard to vary, means that you are seeking all the time to explain phenomena that exist, things that already feature in other good explanations of reality, in terms that aren't arbitrary, in terms of things that can't easily be swapped out for other things. You're looking for this hard to vary quality in your explanations, and when you manage to get that, and testability is one of those things, then you're on the right track. Then you know you're pointed in the direction of progress. Okay, so there's a little more here. Let me read through the remaining parts that I've highlighted. Suppose for the sake of argument that you thought of the axis tilt theory yourself. It is your conjecture. It is your own original creation. Yet because it is a good explanation, hard to vary, it is not yours to modify. It has an autonomous meaning and an autonomous domain of applicability. You cannot confine its predictions to a region of your choosing. Whether you like it or not, it makes predictions about places both known to you and unknown to you. Predictions that you have thought of and ones that you have not thought of. Tilted planets in similar orbits in other solar systems must have seasonal heating and cooling. Planets in the most distant galaxies and planets that we shall never see because they were destroyed aeons ago, and also planets that have yet to form. The theory reaches out, as it were, from its finite origins inside one brain that has been affected only by scraps of patchy evidence from a small part of one hemisphere of one planet, to infinity. This reach of explanations is another meaning of the beginning of infinity. It is the ability of some of them to solve problems beyond those that they were created to solve. Again, here we have another wonderful piece of philosophy, I would call it a discovery. This idea that some explanations have reach, infinite reach, is profound. It turns knowledge into a force of nature. It is the thing that can point itself anywhere in reality and transform that if there are people there that want to do that and have the knowledge of how to do so. So I'll say that again. Knowledge is an entity in the universe that if it points itself at somewhere in reality, it can transform that reality into something completely different, as long as there are people there who choose to do so and have that knowledge. So the knowledge of how to completely transform the Andromeda Galaxy, if it's discovered here on Earth, it is the thing that will transform the Andromeda Galaxy. Which means that knowledge is kind of like a supermassive black hole. If there's a supermassive black hole wandering through the universe that we haven't yet seen yet, although we probably would have because of such things as gravitational lensing, but let's say it's wandering through the universe and no one's noticed it yet, and it's heading towards the Andromeda Galaxy, then if it passes through the Andromeda Galaxy, it could really upset the Andromeda Galaxy. It could perturb the orbits of the stars. It could change the shape of the Andromeda Galaxy. It can do that. No one has a problem understanding that. This idea that black holes, hugely powerful bodies, can eat stars, they could transform a galaxy. But so can knowledge. Knowledge can do what huge structures in physics can do. They can transform things. We've already done it on a very small scale. If you want to explain why it is that a city looks the way it does, there's no point consulting the geology. Well, okay, there is. That geology has something to do with the way a city looks. But what also has something to do with the way a city looks is the knowledge of the people that are there. So knowledge is like a force of nature. It's like erosion, if you like. It's this thing that can pass over physical structures and change them. Let me continue. The axis tilt theory is an example. It was originally proposed to explain the changes in the sun's angle of elevation during each year. Combined with a little knowledge of heat and spinning bodies, it then explained seasons. And without any further modification, it also explained why seasons are out of phase in the two hemispheres, and why tropical regions do not have them, and why the summer sun shines at midnight in polar regions. Three phenomena of which its creators may well have been unaware. The reach of explanations is not a principle of induction. It is not something that the creator of the explanation can use to obtain or justify it. It is not part of the creative process at all. We find out about it only after we have the explanation, sometimes long after. So it has nothing to do with extrapolation or induction or with deriving a theory in any other alleged way. It is exactly the other way around. The reason that the explanation of seasons reaches far outside the experience of its creators is precisely because it does not have to be extrapolated. By its nature as an explanation, when its creators first thought of it, it already applied in our planet's other hemisphere and throughout the solar system and in other solar systems and at other times. Thus, the reach of an explanation is neither an additional assumption nor a detachable one. It is determined by the content of the explanation itself. The better an explanation is, the more rigidly its reach is determined, because the harder it is to vary an explanation, the harder it is in particular to construct a variant with a different reach, whether larger or smaller, that is still an explanation. I'm going to skip over a little more now. it also makes sense to speak of the reach of non-explanatory forms of knowledge, rules of thumb, and also knowledge that is implicit in the genes for biological adaptations. So as I said, my rule of thumb about cups and balls tricks has reached to a certain class of tricks, but I could not know what that class is without further explanation for why the rule works. And I'll stop there on chapter 1. So this idea about the reach of explanations is another phenomenal piece of philosophy, I think. It's up there with this idea that what science is about is not merely testable theories, because they've been common forever. Instead, it's about hard to vary explanations of the physical world. I would say that's my interpretation. But David makes the broader point that what we're actually after in the production of knowledge generally, so whether it's philosophy or history or mathematics, science, any particular domain, what we're after is hard to vary explanations. And the reason that we have been making progress since the Enlightenment through today's Enlightenment is because of a culture of criticism. The culture of criticism where we criticize our best theories that exist at the moment and we improve them, and that enables progress. We're only in chapter 1, and already there are these phenomenal advances in philosophy, phenomenal advances in epistemology, excellent explanations of what our best explanations of epistemology and philosophy are, all illustrated with some excellent science. So that'll do me for now. That's quite a bit of reading, and maybe tomorrow I'll try and get into chapter 2. We'll see how we go. See you.